Okay, recording has started. I didn't hear the recording started. It's interestingly enough, but okay, the recording is going on. Welcome to the study hall for April 24th. We're going to be doing quant again. We're going to have a few more problems left over from the last session of flexible problem solving in multiple choice quant questions. So we've just seen the rules of the study hall, submissions, things like that, the copyright acknowledgement, all of the practice GMAT problems are from the GMAT prep software. In fact, in today's class, all of them are from the GMAT prep software. So there is your copyright acknowledgement. They are copyright GMAC. These are from the free software, which allows them to be reproduced. But remember that problems from the official guide are not allowed in the study. Okay, and also, if you just logged in, remember where your multiple choice answers are located. They are located, graphic will show up on your screen in a second. It's a big graphic. Okay, they're located underneath your name. You'll see a bunch of multiple choice options. Please use those. Please don't answer in the chat box. And with that, let's go ahead and do a problem. So go ahead and give this a shot. You'll see a problem on your screen in the next couple seconds. And please remember where you find multiple choice answer. They'll give you, it's a word problem. It's got more words than normal. It's a longer problem than average. You know what that means. It means that you can take more time than the average time. So I'll give you about between 2 and 3 minutes here. Go for it. Okay, we got 29 people here, and we only got about 10 answers, so it takes another 20 or 30 seconds. But again, at this point, if you are not making discernible progress towards a very concrete goal, then it's time to quit and make a guess. So go ahead and pick something in the next 20 or 30 seconds. Yeah, so you know where the multiple choice answers are. There's still a couple of you who haven't picked something. You may as well just guess, because honestly, here's the class responses right now. We're pretty much all over the place. I mean, no one seems to like E, but other than that, I mean, notice there's 6 people who don't have an answer here. I mean, there's me and the other Manhattan GMAT staff person who's here that we don't count. But 6 of you guys who don't have an answer, remember you gotta guess stuff. That's the way this test works. But okay, remember what the theme of today is. The theme of today is flexible problem solving, which means the focus of today is going to be on non-algebraic ways to solve these problems. And again, this problem we're pretty much guessing as a group, so you're definitely going to want other ways to do this kind of thing. Does anybody know how you can do this problem without using any algebra? Chat box, if you know. No algebra, how can you do it? Doesn't seem like anybody's typing at all. Shy crowd. Remember that the biggest mistake that a lot of people commit on multiple choice is forgetting that the questions are multiple choice. In other words, solving everything all the time as though there were no answer choices, as though you just had to produce an answer yourself. Yeah, there you go. So hanging or hanging, hanking. Yeah, you can back solve it, right? So huge technique. If you're not employing this regularly, then you're leaving some points on the table there. Yeah, you can back solve it. Don't forget what back solving means. Back solving means you basically work the problem backwards. In particular, what it means is that you start from one of their answer choices. So when this is possible, back solving means start from an answer choice. And the great thing about back solving is you don't really have to have a master plan formulated from the very beginning. You can just do whatever you can with the given information. As long as you're following it in some sort of way that's valid. And you just work until you've basically worked yourself into a corner. And then at the end, if everything checks, in other words, if all the information is consistent, then you win. And if anything contradicts anything else, you just try another answer choice. So, I mean, one thing in this problem that sort of annoys people is this. I mean, sometimes people first read that as though it were 1/5 of a foot taller. But if that were what that meant, because it's the 6th year versus the 4th year, so if this just meant 1/5 of a foot, then you would just have a tree that was growing 1/10 of a foot per year, because it would just be half of this. You don't have that as a choice, so that's not what it means. Can anybody tell me what this means? I mean, no matter how you do this problem, you have to interpret the statements in the prompt correctly. Can anybody tell me what 1/5 taller is? It's not 1/5 of a foot. What is it? Yeah, Roby, it's 20%, exactly. I mean, remember that percents are fractions at the end of the day. Like 50% is the same thing as 1/2. In the same sort of way, 1/5 taller is exactly the same thing as saying 20% taller. It's a fifth. In other words, it's taller by 1/5 of the original value. Exactly. So, right. So the height after the 6th year is 1/5 more than the height after the 4th year. What that means is if you say, like, let's say that age is what that means is that if you took the height after the 4th year, then you're just adding another 1/5 of that. So you just, if you combine this, these are like terms. It's like having x plus 1/5 x. So this means you have to get the 6/5 of the height after the 4th year. And that's what the height after the 6th year is supposed to be. So if we go ahead and fill in the rest of that, height after 6th year. So this is what we're going to check if we back solve this problem. So sure. Right, so let's take this to a new page because this page is getting awfully crowded. So let's go ahead and screen grab this and take it to the next page. So here's the problem again. You'll see it in a moment. And then when you see the problem, you'll also see the deduction that we just made. The graphics are loading really huge for some reason. That's why they're coming across a little bit slowly. But okay, there's the problem. And then here's what we just figured out on the last page. The height after the 6th year has to be 6/5 of the height after the 4th year. If you were going to do algebra here, this would be what you would set up as your equation. But if you're going to back solve, this is what you're going to check at the end of the problem. So this is going to be your check. So let's just try to back solve from some choice. Might as well start in the middle because 1/2 is a really nice number too, sure. So let's just make a table. So let's say the height is to start with, so it's planted. And then after year 1, after year 2, after year 3, after year 4, after year 5, after year 6. I mean, you can also calculate these by, multiplying it and adding it, but I would rather just do it out like that. So if we try the middle choice here, let's see how that works out. So when the tree was planted, it's 4 feet tall. After year 1, it's 4.5. After year 2, it's 5, 5.5, 6, 6.5, 7 feet tall. So notice this is supposed to be a ratio of 6 to 5, but it's actually 7 to 6. So after the 6th year, it's 7/6 of the height after the 4th year. Now here's what you want to do. If you don't know what this means right away in terms of which way you should go, then you should just plug in another choice and see what happens. But if you can think about it, because 7/6 is less than 6/5. So because this is 1 and a 6th, and that's 1 and a 5th, which is bigger. So that means the tree is not growing fast enough because it's not growing on itself in a ratio high enough. So if you realize that to start with, then you know that you have to eliminate the smaller values as well. If you don't realize that within a few seconds, don't sit there and keep thinking about it. Just plug in another number and watch what happens. Because if you plugged in A or B, then this ratio would get even smaller instead of bigger. And then you would know you're supposed to go the other way. So, okay, well, 2/3 is a nicer number than 6/5. So let's just try that and see what happens. So it's still 4 feet tall when it was planted. Then it was 4 2/3, 5 1/3, 6, 6 2/3, 7 1/3, and 8. So you're looking at this ratio. The ratio is 8 to 6 2/3. Common denominator-wise, that's 24/3 to 20/3. So it's the same ratio as 24 to 20, and that's exactly the ratio that we want. So we win. This is a thing. You can do it. That's the ratio we want, and so that is the answer choice we want. So you can back solve. Like in this problem, you may, if you hit a wall with this, then you're going to hit a wall with it anyway, and there's not a lot you could really do other than slow down and be much more careful about the way you interpret it. Yeah, the 6/5, we derived that here on this page. It's 1/5 more times the original height. So it's the original height plus 1/5 of the original height. Maybe it'll be more clear if I take these out and call it original height. You want it to be the original height plus 1/5 of the same original height. And so that works out to be 6/5 times the original height. I mean, it's the original after the 4th year. So let's just say 4th year. It's not the when it was first planted height. So maybe original is a dangerous word to use here. But it's the 4th year height plus 1/5 of the same value. That's what 1/5 taller is. Or 20% taller, whatever you want to call it. So you can back solve it. It's a thing. It's possible. You still have to interpret the statement correctly. So a little bit of generic advice as far as that is concerned. You got to slow down when you read the problem statement. Slow down. If you read the problem statement more carefully and more slowly, you will actually finish the test faster than if you rush. And this is one of those things that sometimes people just don't believe when I say it, but it's one of those, like, I think it's the Marines who have a saying of slow is smooth and smooth is fast, and that's pretty much what this is here. Like if you read it really fast, you're going to have to read it a lot of times, which will ultimately take you longer than if you read it more slowly and reflectively and only have to read it once. So there you go. We're going to take a look at a more traditional solution now, but again, just make sure that back solving is in your book of techniques. Make sure that it is a thing. Back solving. There you go. Okay. We can also take a look at a traditional solution to this. Again, the main focus of today is on expanding your repertoire of methods where you're going to, be able to do less traditional solutions like back solving. But at the same time, the main goal of everything all the time is just to accumulate as many methods as you can accumulate. So that's what we're ultimately trying to do here. So if you were going to do a more traditional algebraic solution here, so there's a couple ways that you can do this here. But you probably want to use the fact that it was 4 feet tall to start with. Although, do you really have to do that? Maybe not. We'll see here. But let's do it that way anyway. Let's say that x is, what is our variable going to represent here? Someone tell me. If you're going to do this algebraically, you got to make a careful choice of variable. What's a good choice for a variable? Everybody. So a few people typing. I mean, okay, you can call it whatever letter you want, but you could use, do you want to use h as a variable, though? Not so maybe. Although, if you think about it, what does this really all depend on at the end of the day? I mean, the height is not, I mean, there's these terms that statisticians use, independent variable, dependent variable. This is the, if you think about it, when you say independent variable, that's the thing that actually determines everything else. And the dependent variables are the things that come from everything else. So like if a kid grows to be a certain height as the kid gets older, then time is the independent variable and the height is the dependent variable. You want to think about what is independent here. You want to think about what is ultimately what determines the other thing. So, I mean, as far as what letter like always X first choice. I mean, Romeo, it sounds like you're just saying what letter to use as opposed to using other letters of the alphabet. If that's what you mean, then maybe. But I mean, you've got two quantities here to consider. Like there's the height that the tree grows every year. And then there's also the actual height of the tree. And the question is, which one of these depends on which other one? I mean, this is the question that you want to answer when you want to determine what to make a variable and what not to make a variable. This is the operative question here. And I mean, you really don't want to make a variable for the dependent quantity because then you have to reverse the formulas. Like, for example, the area of a circle depends on the radius. You don't really think of it as the radius depending on the area. So your variable is r, and it's easy to write a formula for a in terms of r, which is pi r squared. You know, if you made a the variable, then the radius would be like square root of a divided by pi, which would just be terrible. So yeah, right, the actual height depends on the growth and not the other way around. So it's going to be easier to make this our x because this is independent. And then the height of the tree is a function of the other thing. It's a function of how much the tree grows every year. Exactly, so that's a good call. So this is what you want your variable to be. You want your variable to be x is the growth of the tree every year. Because then when the tree is first planted, it's 4 feet tall. How tall is it after 1 year? Chat box. Yeah, see, it's easy to write these formulas now. If you made the mistake of letting h stand for the height of the tree, it's going to be really hard to do that. So, but you just keep adding x every year. So it's not 4 times x, because you're not multiplying anything. It's growth by x. It's x more feet tall. You know, it's like if your kid is 3 inches taller after another year, it's x plus 3 inches. It's not times 3. So after 2 years, it's going to be 4 plus 2x, etc. So the two numbers of years we actually care about are after 4 years, which is going to be a 4 there. And then after 6 years, it's going to be a 6 there. And then you just want to import what we figured out in the last part, which was the height after 6th year is 6/5 of the height after the 4th year. So that's what we figured out last time. So we can just import these expressions now. So after 6 years, it's 4 plus 6x, and that's 6/5 of 4 plus 4x. So you've got 4 plus 6x, leave that alone for the time being. 6/5 times 4 is 24/5 plus 24/5x. Okay, I mean 24/5 is less than 6, so take the 24/5 over here to give you 6/5 left. And then 4 is 20/5, so subtract that. You can multiply both sides by 5. And so then x is 4/6, which is 2/3. 2/3 of a foot per year. How would it be phrased if the formula was increased by a constant factor? Well, this might take you out of the realm of math that works in a test. Let's try it. First of all, let's see if there's any questions about what's on the board. If anybody has any questions about this, feel free to type them in the chat box. I think one person might be typing, but I think that person has had some stuff in their chat box for a while. So if that question pops up, we'll see it. But okay, so let's take this over to the next page and see what this question is that we've got going on here. Okay, here's a problem again, and then the question that was asked was this. How would it be phrased? Constant factor, meaning you're multiplying by a number every time. So this is also another little piece of vocabulary that they might throw at you. I don't know how likely it is that they would, but they certainly could. Factor means you're multiplying by a number, not adding it. So this would mean, again, just make sure the vocabulary is not what gets you. This means multiplied by the same number every year. I mean, that's not really how living things grow. I mean, things grow less as they get bigger, but let's just put that aside for a moment and just pretend that it did do that. That would mean that when it was planted, it would be 4. So then after 1 year, it would be 4x. And after 2 years, it would be 4 times x. So it would actually be 4x squared, etc. So after 4 years, it would be 4x to the 4th. And after 6 years, it would be 4x to the 6th. So this would wind up being 4x to the 6th equals 6/5 of 4x to the 4th. In that case, we could just actually, yeah, I mean, you get some horrible number out of this, but if you you can cancel the 4s. So you get x to the 6th is 6 and x to the 4th. You can divide by x to the 4th because we know it's not a 0 factor. So you would get the square root of 6/5. I mean, that's going to be some horrible, terrible number, but if they just made it some other fraction so that it wound up being a perfect square, like if instead of 6/5, like instead of 1/5, if they made this, say, 9/16, so that this wound up being 25/16, then you would get 5/4, which could be decent. But with these numbers, you would get this terrible, horrible square root thing. What happens if we end up going that route? What is that route? I don't know what route. Help me out there. I mean, yeah, if you have to guess, sure. I mean, if you don't, because again, if you misinterpret the problem statement, then you're gonna not really have a lot of options other than to guess. Because I mean, a correct interpretation of the problem statement is indispensable. You're not going to be able to solve the problem if you have the statements not meaning what they should. Yeah, that's why, again, this advice is crucial here. Slow down. If you misinterpret problem statements, it's probably because you're going too fast. So, yeah. But again, this is not a repeated factor. I mean, it's constant amount. Constant amount means constant amount. It doesn't mean constant factor. So just make sure that you're interpreting your statement literally. If you really didn't know that, then just get it as a takeaway, put it on the flashcard, constant amount versus constant factor. What does that mean, right? Constant amount means you're adding some quantity every time. Constant factor means you're multiplying by something. So yeah, you just chalk it up to experience, you learn it, keep it in your head, and then you beat it next time. That's what we do. Okay, any other questions about this problem? Throw them up there. If not, let's try something else. Let's try another problem. Sam, if you're okay with algebra, the goal, let's just make sure we get this on the board because it's kind of the whole point of doing these sessions that we've been doing lately. So remember that your goal here is not to have like one method that makes you get a gold medal. I mean, because okay, if you're what you're calling okay by algebra, like if you can do it by algebra, but I can do it by algebra and by back solving, then I win. I mean, it means that I'm going to get more problems than you will. Because remember that no two problems on the GMAT ever work the same way. So just make sure that you understand two separate processes, which are doing the problem and reviewing the problem. These are not at all the same. And you want to make sure you appreciate the differences. Doing the problem is actually a simulation under timed conditions. Reviewing the problem is not a simulation. It's when you go back and study and try to get takeaways. And this is totally untimed. I mean, you can spend as long as you want on a problem. So it's just different. It's different. It's a different way of thinking. Like when you're doing the problem, if something comes to mind, just try it. If it's not working, then you should quit immediately. You should not sit there and stare at things. And you probably want to try methods with which you are more comfortable first. Okay, on the other hand, the goal of reviewing the problem is exactly the opposite. I mean, you have one goal here, which is to collect as many methods as possible for solving the problem. You should not have any sort of preference here. In fact, when you review problems, you should preferentially review methods that you don't like as much. Because that's the whole point. I mean, you're not going to get any better at this thing if you just practice the methods that you are already good at. I mean, there wouldn't be much point there. You know, it's like anything else. If you're an athlete and you're not very flexible, then you have to spend more time stretching than other athletes, not less. I mean, you might hate it, which is probably why you're not flexible in the first place. But that means you have to do more of it if you want to, you know, round out your skill set. So, but your goal is just to collect as many methods as you can. And this is where you don't want to quit right away. Like review is where you want to struggle with methods you find harder. See if you can get them to work. See if you can learn to make them work. It's not like you're, you know, under time pressure where you just want to let it go. I mean, this is where you actually learn to get these things to go. This is, I mean, so I'm glad you asked this question, but when you're doing the problem, yeah, of course you should. But then when you go back and review later, then your job is a different job. Okay. How would, Luis, I don't know what you mean by that. How would a kid solve this if you create a table and start? You can't, if start with your own rate means make up a random rate. Okay, were you guys on this page? Okay, if not, then you're on this page now. So here's all the things we've been saying. Doing the problem versus reviewing the problem. Doing the problem is simulating. Doing the problem is time conditions. You want to let go of stuff right away if it is not working, and you want to favor things that you're more comfortable with. All right, but the point when you review the problem is to actually build up the methods that you are less comfortable with. The less comfortable you are, the more time you should spend reviewing it, which is, you won't like it as much. I mean, everybody enjoys practicing things they're better at because, you know, it feels really good to be good at it. But when you're talking about building your skill set, it's not how you do it. So, okay. This, Luis, I don't really understand what you're asking. I mean, if when you say start with your own rate, if that means make up your own rate, then you can't make up your own number because there's a correct answer to the problem. The correct answer is 2/3. So if you make up a rate other than 2/3, it's not going to be correct. And making up a rate, maybe I'm not understanding what you're saying, but making up your own number is something you can only do in problems where you don't find a correct answer. So if that's, I'm not sure if that's what you're asking, but again, you can clarify. In the meantime, let's put another problem there on the board. Let's try something else. If the question didn't say the tree was 4 foot tall, then you wouldn't have an answer the same way. It would be a totally different problem. What you might want to do in that case is, like, take it home and play around with it and see what changes if that happens. Like, I mean, if the tree is a different height to start with, then the growth rate is also going to change. But you can take that home and mess around with different variations on this problem. In fact, if you make your own variations of this problem, you can learn a lot more than if you just passively solve other people's problems. So yeah, try that. Try to make your own versions of it, for sure. See what you can discover about how the numbers interact with each other. It's kind of an interesting exploration you can do. Okay, let's move on to something else. Discrete two processes again. Yeah, I think that was this screen. Okay, that's discrete two processes. Let's do that maybe 5-10 more seconds. Just if you can just screen grab it or something, then let's move on to something else. Okay, let's move on to something else. How about that? Okay, give that a shot. Here's a timer. Go for it. Remember to read the problem slowly and carefully and make sure you understand what the words in the problem statement are referring to. Okay, there's 26 of you here besides us, 27 of you here besides us, and there are only a few who answered, but now you're starting to answer. Let's go ahead and pick something, please, ladies and gentlemen. Okay, we still Ashish, Gael, G, Vega 0884, and Romit and Triumph Kai. Go ahead and pick something. Remember how this test works. You got to pick a choice that is a choice. And I can't make you, but they can. So just make sure that you get used to it. Okay, let's take a look. If you look at the results here, we've got two favorites, although we are very divided. It's a very bimodal answer distribution here. People like B and people like E. Are the answer choices correct? Well, one of them is. 4 of them are wrong. That may not be what you're asking me, but there are 4 wrong answers and there is 1 right answer. So, yeah, let's take a look. If you meant something else, then go ahead and clarify, please. If you did mess up somewhere, it may have been in reading the original problem. So, what is the medallion? Like what is how much of this is the medallion? So yeah, well, let's see, right? It's all of you guys are mentioning the black circle, well, except for the last commenter. But I mean, if you think about it, if you think about what a medallion is, I mean, the medallion is not going to stop where the white part stops, because a medallion is the thing that you wear around your neck on a chain or something, right? So I mean, you know that the medallion, just sort of using your own understanding of what medallions are, you know that it's definitely going to include the outer part. But let's just read about what it says here. It says, a circular piece of colored glass surrounded by a metal frame. So it's the whole thing. Like, in other words, they're including the glass, which is the inner circle, and then they're also including the metal part. So if they weren't including both of these things, they would not have said circular twice. Like if they just meant the glass part, then they would have said a circular thing surrounded by a frame. They wouldn't have said a circular thing made up of a circle surrounded by a frame. Then this means that this circle is not that whole circle. So there are lots of clues here. But again, slow is the name of the game. You want to be really slow and really careful. Really careful. So the R centimeters is all the way out to the end. So if you want to run that all the way out there, that's going to be the R. R is from there to there. So this color code. And then the S is just the width of that frame, which is a pretty small width in this problem. So it's just the rim, width of the rim. So that's S. And again, if you worked it out the other way, you're not going to get something that works. So you can always pull it out of the fire by just realizing, oh, it must have not been what I thought it was at first. It'll take you a little more time, but it's not unsalvageable. Okay, let's take a look. How can you do this problem that is not algebra? Especially in a problem that looks like this. I mean, there are R's and S's all over town here. So this should be pretty much screaming at you that you can do one particular thing. What one particular thing is that? I mean, what does it mean when there are still R's and S's? Yeah, I mean, you can make up your own numbers. So plug in your own numbers. I mean, because again, what it means, because these people are not weird, deceiving tricksters. Like, if you could find out what R and S were, like if those were numbers at the end of the problem, then they would not still be in the choices. You know, like for example, if R turned out to be like 10 and S turned out to be 8, then this would not say R minus S quantity squared. It would just say 4. It would just be 2 squared. They wouldn't keep the letters if you knew what they were. They would simplify it. So what this means is like if the answer choices keep the letters, then you don't ever find out what they are. So you can pick them yourself. Because what that means, if you don't find out what they are, then that means that the problem has to work for any choice of those numbers. Because if it didn't, then there would have to be some way to solve it if there were only particular solutions. So let's just make up numbers. Let's just make up our own value for that. So, I mean, we want to make it look something like the problem. It doesn't have to be exactly to scale, but we should make it look something like what's there. So someone give me a number for R and a number for S. And 10 and 100 is kind of big. I like 5 and 6. I mean, remember, you're going to have to square these things because these are radii. I mean, you're going to have to find areas of circles by doing pi r squared. So, I mean, when you say 5 and 6, you're probably thinking that this part is 5. So let's let S be 1, and let's let R be 6. So that would mean S is 1. It wouldn't mean S is 6. So, sure. So let's let S be 1, and let's let R be 6. So then the area of the metal frame is the difference between two circles. So using the two, it's the big circle minus the small one. It's the black circle minus the white circle. So that's the area of the frame. The metal ring is big circle minus small circle. So the big circle would be pi times 6 squared. So, and then the small circle would be pi times 5 squared, because that's the 5, right? It's what Anthony is saying. It's the part between the 6 and the 1. So 36 pi minus 25 pi, and that's going to be 11 pi. And then we want to plug in the choices and see if we get 11 pi. So A is going to be 25 pi. It's pi times 5 squared. So that doesn't work. B is going to be pi times 36 minus 1. Not 11 pi. C is going to be 2 pi times 6 minus 1. So that's 10 pi. Close, but no cigar. It's awfully close, but it's not the number that we want. D is going to be pi times R is 6 times 12 minus 1. That's huge. That's 66 pi. That's actually bigger than the whole thing. And then E, because the whole thing is only 36 pi. And then E is going to be pi times S, which is 1 times 12 minus 1, and that's the answer that we want. So it's nice. I mean, what this is going to let you do, like the main advantage of plugging in your own numbers is it allows you to completely circumvent whatever algebraic work you have to do in the problem. Because generally when you have numbers to work with, there's not really any calculations that are harder than others. There may be more annoying calculations, like you might have to do arithmetic that is mildly unpleasant, but it's not going to be like hard. It's not going to be getting lost kind of thing. And at worst, it'll be annoying with numbers that are not so hot. But it's still going to be grade school math. So that's the advantage of plugging in your own numbers. It lets you sidestep a lot of other stuff. Any questions about this? If not, then let's take a look at a more traditional solution to this. But again, remember that the point of today is the non-traditional solution. So when you walk out of here, make sure that plug in your own numbers is in your repertoire. Make sure it's a thing that you can do. Make sure it's in your tool belt and that you are not afraid to whip it out and use it. Okay, here is, let's just take the essentials from that last problem. Here's the diagram. And then here's the, we're not reproducing all of the words in the problem. We know that we want area of the metal ring to be big circle minus small circle. And then we know what we have in terms of R and S. So again, I don't know why these things are coming out of the board so huge, but let's resize them. Okay, that's what we want, and then don't forget which things are S and which things are R. So that color is R. Oh, that went upside down. I didn't mean to do that. Okay, there we go. Interesting. Okay. And then you want the big circle minus the small circle, and then last, let's take the answer choices, because you're going to want them, if you're going to do algebra, you're going to want them as is. So there's your answer choices. Okay, so this is going to be just straight algebra. It's going to be a little bit annoying, but at least it's going to be, you'll see what the value of plugging in the numbers is here. It's going to let you not have to do this. But in any case, the big circle is pi r squared. So, and then, what's the small circle area? Anybody tell me? Like, what's the radius of the small circle? Yeah, right. You got to figure out that the radius of the small circle is going to be the difference between r and s. So that right there is r subtract s. So r minus s. So it's going to be pi r squared minus pi times r minus s, quantity squared. So you're going to wind up with something that looks like this. So there, again, sorry for making it so big. Okay, so that's what you wind up with. You wind up with that. So if you simplify this, you just have to do a bunch of annoying simplifying. So that's going to be r squared minus, if you multiply that out, you get r squared minus 2rs plus s squared. And that's all in parentheses, and that's all being subtracted out. So it looks like this. And then these guys are going to cancel, because that's going to be pi r squared minus pi r squared. And so all you're left with is the minus 2rs, which winds up being positive 2rs. Still have a pi out there. And then you have the s squared becomes negative, because again, you're subtracting that whole quantity. So your final answer looks like this, and then if you pull out the s, then you get exactly the expression that is in choice E. And so there you go. Any questions about this? It's the more traditional solution. Hopefully you can see the advantage of plugging in your own values here, which is that you don't have to go through this kind of thing. This is not so terrible. I mean, if this is very off-putting to you, then what you would want to study this sort of algebra so that it's not. Which would basically just involve going to your local library, just grabbing an algebra book and just doing practice with it. But you want to be equally fluent in both of these methods. You want to be able to rip this off with no trouble, and also to rip this up with no trouble too. You know, they're both pretty efficient if you can make them fly. And remember, your goal of review is just to collect both of them. You want to be greedy. You want to just collect as many solution methods as you can. Any questions, feel free. Is there a third way? Not that I can think of right away, but I don't really want to say no, because, you know, since I say no, the answer will be yes. But, yeah, the point of reviewing it is to try to figure that out, right? I mean, I can't think of a third way super right away, but other than to realize, you can look at these, like you can eliminate D because you can realize that it's bigger than the whole medallion. The entire medallion is pi r squared. And R is bigger than S, which means that 2R minus S is bigger than R. So then that means that D is actually pi R bigger than R, which is bigger than pi R squared. So I mean that would be enough to eliminate D. But as far as from where I sit, the only thing you can eliminate there is D. You can eliminate C because it's not an area in the first place. Like C is not, I mean, if these things were in inches, they're in centimeters. Okay, like these are all square centimeters except for C. Like C would just be in normal centimeters. So that couldn't possibly be an area because it's not in area units. It's not in square centimeters. So, I mean, that's the third. If you want a third way, actually the question asker is not even here anymore. They got logged out. But If you guys want a third way, I mean, you can eliminate C and D like that way. You can eliminate D because it's bigger than the whole thing, and you can eliminate C because it's not the right unit. But as far as A and B and E, I'm not seeing anything right away. That's not one of the first two we just did. But yeah, I mean, maybe you guys can think of something else. It's part of beating this game is to come up with lots of cool, creative solutions. Absolutely. Okay, let's try that. Okay, here is some time. All right, ladies and gentlemen, let's take about another 20 seconds max if you need it. Let's get something down. Let's get a choice. Let's just pick one. All right. Was anybody here in attendance at the study hall 2 sessions ago? So that would have been, I think, 5 weeks ago, March 20th. Did anybody see that session? If you did, was anybody here for that? Okay. A couple of names that look familiar, but there are also names that a lot of people have. So like there's a lot of Ashish's and there's a lot of Jameses and Heathers in the world. But okay, because if you were not here when we did, in fact, let's wait for that discussion. First, let's talk about how can you do this problem if you don't see the cool trick. Because there is an algebraic trick that you can use here, which is to use factoring patterns. But what if you don't see that? Does anybody know what else you can do that is much more low tech, much less high tech, much less cute, much less elegant, but it can still very much be done in the time that you have? I mean, that's the trick. The 1,000 plus 1 thing, although even that is more than you have to really do. That stuff is still awfully lots and lots of work. You can do that too, but the trick that I'm thinking of is simpler. Let me just show you what the trick is. All right. I mean, you guys have the right idea in mind. You're not necessarily using it super efficiently. But the trick is to use this formula. This is what Ranul points out. Because this factors into the first thing plus the second thing times the first thing minus the second thing. But wait a minute, you can notice that this is actually the exact pattern that this has and the exact pattern that this has. So you can factor both of those out. So that's just going to be 1001 plus 999 times 1. Like in the top part, A is 1001, and B is 999. And then in the bottom part, A is 101, and B is 99. So you can just break those up into those things. You don't need to break them up into thousands and hundreds and ones and tens. So those are really, really pretty numbers. I mean, those are 2,000 times 2 over 200 times 2, which the 2's are gone, and so that's going to be 10. Okay, so this is the algebraic trick that I was referring to, but there's another way that you can totally do this. within 1 minute, even if you don't have any idea about this trick or if you don't see these factoring. Yeah, you can just do it out. Do not be afraid to just do it out. I mean, okay, so what I was talking about with the last session, in the last session, in 2 sessions ago, we had this problem which was, to be totally honest, which was way more scary looking than this one was. I'm going to go ahead and upload a picture of that to the board. You'll see it show up here in a moment. This was from 2 sessions ago. So you'll see the problem there in the top left corner. I mean, this is a much, much more scary looking problem. It's still uploading for you guys, but you'll see it shortly. Okay, it's starting to appear for most of you. And if it's still loading, it should not be loading for too much longer. Okay, I mean, the problem, this looks so much scarier than what we're looking at right now. But if you just, and I mean, honestly, if I were looking at this problem, I would not, there's a similar algebraic trick to what you see on the current problem, but I would not, there's no way that I would see it in the time allotted here. There's just no way. So what I would do is just pick up the shovel and dig. Just do long division. Don't complain, just do it. So if you move these decimals over, that's 9999.999 over 10,001, and look how nice this division works out. I mean, you're dividing by 10,001, which means there's no carryovers. It's very easy to see the multiples. It's really nice at the end of the day. So that works out to 0.9999. Same thing, this is just 10,003 is a really nice number to divide by. So we just worked it out, and it worked out to 0.9997. This is doable in a minute flat. You can do it. The only way you're not going to do it is if you talk yourself out of it. Don't let it happen. I mean, don't erect roadblocks in your own path, which is what people do all too often. So if you want to, we did also do the algebraic trickiness. If you want to see that, you can check out the recording of this. It's in the March 20th study hall. But the point is that if you don't see the high-tech method, just do the low-tech method. Just grind it. I mean, they engineer these problems so that this will not be terrible. I mean, they are really creating a test that favors the person who just shoots first and asks questions later. That's what this test is all about. So by comparison, this is genuinely tame. I mean, 1001 squared is really not so bad, right? It's 1001 times 1001. Let's just do that out. So 1 times 1001 is 1001. And then we can just skip to, because these next 2 places are 0. And then that's going to be 1001 as well. So that lines up here. So that's going to give us 1002001. And then if we do 999 times 999, I mean, it's not as beautiful as that, but at least you get the same number all 3 times. So 9 times 9 is 81, carry the 8. 9 times 9 is 81 again, but that's plus 8, so it's 89, carry the 8. It's 89 again. And then that's 8. And then these are also going to be the same. So that is going to work out to, that's going to be a 1, a 0, a 0. If you add all that up, then you get 998001. Okay, so then, and then if you do the math on the bottom, it's actually the same math, except you don't have as many places of 9s and 0s. If you work it out, what it is eventually going to look like is this. And again, this is very doable. You just have to not question it. You have to not sit there and stare and be intimidated by it. You have to just do it. And then those are really, really nice subtractions. I mean, if you subtract those, the 001s are gone, and you just get 4,000, and the 01s on the bottom are gone, and you just get 400. That's not too bad. This is, I mean, even if you are totally not fast at this, this is still very doable in way, way less than the average time. So there's also other ways to multiply 999, Peter is sure. There's going to be a lot of arithmetic tricks out there, and if you know them, I mean, that's what you can review as well for that sort of thing. When you review the problem, you should ask yourself questions like what Pete is asking. You should say, are there other ways I could have done these steps more efficiently? But if you don't think of that in real time, then you just grind it out and smile. That's what you do. Like, in other words, you shouldn't sit there thinking during the process about whether there's a more efficient way. Like, if something immediately pops into your head, then do it. But if it doesn't pop into your head, don't waste the time to sit there and think about it. Just do it the old-fashioned way. It's not like it really takes that long. So, you know, but yeah, it's a valid question to be asking in review so that you can learn stuff and then bring it into the next question with you. So either way, it's 10. But, you know, this is another alternative method. It's not as glorious as a lot of the other ones, but it's just a good old-fashioned arithmetic. Never goes out of style. I mean, don't forget that you can do it. A lot of people are very opposed to just getting the old proverbial shovel out and digging. And you want to make sure that's not you. Because, I mean, even a problem like this, pretty humble in the face of good old-fashioned fifth-grade arithmetic. I mean, they do this on purpose. This is not an accident. Really, it's not. So they, would I have skipped that problem? No, I would have just gotten out the shovel and dug. I would have just done the arithmetic. We just did it. So. Yeah, remember it doesn't matter where in the exam the problems are here. And also don't forget the time management. If you quit when you are stuck, if you are not shy about letting go when you're not making progress, you won't feel time pressure at all. Like, time pressure is only a thing when you are hanging on for too long. It's from 2 sessions ago, so it's like 4 or 5 weeks ago. March 20th is the date that it's from. Okay, let's look at one more problem. And then we're out of here. Let's take a look at this guy. Right there. Go for it. Here's a timer. Have fun. All right, let's pick something pretty soon here. Again, you know, it's just the kind of test where you got to keep moving. So let's pick something, please. All right, let's take a look at this thing. The picture is not to scale, but we still know some things about it. And I mean, we can try to imagine what this would look like, but we can reach certain conclusions without even necessarily having an accurate diagram. And this, as far as other alternative methods, you can just use a combination of visualization and common sense. I mean, often these things are separate as well, but when they combine, they're especially powerful. Like 15 feet in this problem is this entire oval-shaped thing that goes all the way around. Are we all on that page together? Like, we all understand that 15 feet is the entire circumference of this belt. Okay. So, well, let's talk about it. So, how long is how long is this? Like if we take this half about, how long is that? Okay, that's 7.5 feet. And then what you want to do is just use your eyes to compare that with what you want, which is just the distance here. So now if you think about this, if we want something we can compare to that 7.5 feet, let's just go ahead and extend this thing out. So in red, we're going to go ahead and extend that out all the way to the ends. What do I know about the red thing? I don't know exactly how long it is necessarily, but what do I know about it? I mean, how does it compare with the purple thing? The red thing is, they're talking about the red thing. The red thing is definitely shorter than the purple thing. I mean, remember that straight lines are the shortest path between 2 points. Alternatively, just imagine that the purple thing is a piece of string. And that's the common sense part. Like imagine if you had a piece of string shaped like this and you pulled it straight. I mean, if you pulled that piece of string straight, then you would very clearly get a length longer than the red thing, because even when it's kinked up like this, it still covers the whole red thing. So the red thing itself is less than 7.5 feet. And then the green thing is if you're taking off a foot in diameter, so that's half a foot here and half a foot here. So the green thing is exactly 1 foot less than the red thing. So green is 1 foot less than red. So that means that it's less than 6.5 feet. I mean, this is absolute. It doesn't even matter if our picture is distorted, because we know the purple thing is clearly longer than the red thing. I mean, if we wanted a more accurate estimate, then we would have to try to draw the picture to scale, which might be time-consuming. But you would have to figure out how the diameters of the circle relate to the overall length. That's not super easy. But the green thing is less than 6.5 feet. Okay. Well, let's just see how long these things are. I mean, 5 pi over 4, pi is about 3. So this is approximately 15 over 4. So that's approximately going to be about 3, a little bit less than 4. So that's okay. That's an okay value. Forgot about A. That's approximately 15 minus 3. So that's approximately 12 over 2. So that's about 6. This is okay. I mean, to me, this looks more reasonable because the red thing is not that much shorter than 7.5. The red thing is probably about 6 or 7, which means the green thing is probably about 5 or 6. So this is a better, if you look with your eyes, this is a better approximation. Because it just is, right? I mean, but okay, 15 minus 2 pi, this is approximately 15 minus 6. That's approximately 9. I mean, that's longer than the purple thing. No way, guys. No way at all. Can't be. Impossible. 15 minus pi is even bigger. This is approximately 12. No way, guys. It's not reasonable. And then E is about 6. Now, so these are pretty good. I mean, B is too short. If you look at that with your eyes, you can tell that B is too short. So we're down to A and E. But if you look at E, I mean, E should trouble you. And it did because nobody actually picked E. I mean, here were the polling responses. So at least you guys saw through choice E. Because the problem with choice E is that and choice B for that matter as well, is that they don't depend on the length of the conveyor belt at all. I mean, it should be clear that you're going to have to subtract something from 15 or from half of 15 here. Because, if you made this conveyor belt 40 feet long, you would just have extra length here, which would be part of the 40. So you should definitely have to have a 15 somewhere in this formula. So like 2 pi would just be the length of one circle, which that doesn't take into account the straightaways. So E has the right size of answer, but it just doesn't take into account the stuff that's in the problem. So that leaves us with A, just by using a combination of looking at it with our eyes, using a little bit of common sense. You know, the purple is longer than the red is basically common sense. And then just thinking about this doesn't really work up the entire problem. I mean, you can solve it. It's kind of neat. It's pretty cool stuff. So those are also alternative methods. They are things. I mean, we're going to close out here by looking at a more traditional solution to this. But again, don't forget what the ultimate point of this lesson is, which is to diversify your proverbial portfolio. We eliminated B because it's too small, right? Like if you look at this, if this was less than 4, then the green thing would be less than 5. And I mean, again, think about your piece of string. I mean, the red thing is not that much smaller than the purple thing. You know, it's not only 2/3 of it. Especially because if you think about what this problem actually looks like, these are 1 foot in diameter. So what that means your problem really looks like is the circles are much smaller than we've drawn them. Like what this problem is actually going to look like is it's going to be a lot more like this. Like there's going to be a lot more straightaway and a lot less circle, which means that the red and purple are even closer together than they look like they are here. But yeah, B is too small. And if you don't see that, you can try drawing the scale. That'll let you do it too. All right, closing. Let's go ahead and do a more traditional solution to this thing. So what you don't want to try to do is jump into variables and stuff too early here. You want to make sure that you understand what the heck is even going on here first. As always, the first step is always try to gain an understanding of it. So here's the problem again. Let's take a look at a more traditional solution. Traditional in quotation marks because, you know, it all depends on what your traditions are. But so this is the thing that we want. Let's go ahead and color code it the way we did before, which was green. So that's the want. So let's just say that the thing that I want, is X. The key realization to make here, and you don't need to memorize circle relationships to figure this out. You can just look at it with your eyes. But you can realize that this part of your straightaway and this straightaway here, those are actually the same as X. I mean, some people will actually memorize like relationships about how this is going to hit at the exact top and bottom of the circle, but you don't need to memorize that because you can just look at it with your eyes. And it should be pretty clear that the intersection points are going to be the top and bottom of the circle. So that means that this is the same length as that, which you can see with your eyes. And if you're worried about the not drawn to scale, then you can draw it a couple different sizes, and you'll notice that it always does that. If one circle were bigger than the other one, it wouldn't do that. That would be a whole different animal. But if they're the same size, then this is basically a giant rectangle here. So then those are X. And then if you think about this and this together, those make up exactly 1 circle of diameter 1 foot. So the purple parts are 1 circumference, which is pi d. So that's pi times 1 foot, which is pi feet. So you have pi feet plus the green parts, which are 2x. And that's going to be 15 feet, because they tell you the whole conveyor belt is 15 feet. So you solve for x. 2x is 15 minus pi. So x is 15 minus pi divided by 2. And there it is. Again, the main point of today is that you can also use your friend's visualization and common sense. Those are also things. All right, I'm going to go ahead and kill the recording here. Thank you, guys. Thank you for attending, as always. Just a heads up about the schedule of the next couple of sessions. Long story short, I'm going to be out of the country for a little bit, so we're shoving 2 of them together to make up for that. So the next 2 sessions are actually scheduled for May 8th, which is what you would expect it to be, but then the next section is going to be May 15th rather than May 22nd. And then after that, not till June. So there's going to be 2 consecutive weeks of this, so you have to suffer through hearing my voice for 2 weeks in a row. If you could last through it. Okay, I'm going to go ahead and kill the recording, and thank you for attending. Good night and good luck.